Good morning, everyone. Let's start. So in the previous class, we looked at an example of how to construct the Shannon code for a given distribution. And then we saw that the Shannon code, of course, achieves an expected length of at most entropy plus 1 bits. And we also saw that no matter how we choose our code, as long as it is prefix free, the expected length is always going to be greater than or equal to h of x. So the minimum expected length that we can expect for a given prefix-free code is h of x bits. So the goal is to get as close to h of x plus as possible. We saw that we can achieve entropy when the source is dyadic, but otherwise it is going to be strictly greater than h of x. Right? And we also saw through an example that the Shannon code is not always optimal. It is always possible to do better than the Shannon code in many cases. All right. Uh, and then we had a discussion about coding symbol-wise versus coding block-wise or coding long sequences. And we saw that if we did block-wise coding, then we can achieve an expected length of somewhere between n times h of x. And sorry, if we do it symbol-wise, then we can achieve anywhere between n times h of x and n times h of x plus n bits. Whereas if we do blockwise, then we can sort of lose this particular factor, becomes h of xn, and it's between h of xn and h of xn plus 1 bit. So in terms of the minimum expected length, coding blockwise is always better, but in terms of computational complexity, blockwise is of course going to be harder. And of course, you also have to have a good estimate of the joint distribution Pxn, which for large n is going to be hard. Okay. So any questions from the previous class? Any questions? Okay. So so another sort of aspect uh, that occurs very frequently is that now so far we have assumed that the distribution is known exactly, right? We have assumed that Px is known exactly, right? But but this is not always the case. What if we don't know the joint distribution correctly? Suppose that we have a rough estimate. Suppose there is an error, right? An error in estimating meeting Px. So how would you estimate Px? You're given a long sequence xn. Assume that you're doing symbol-wise coding, of course. So one proxy for Px is that you just count the empirical frequency, right? So you look at mu xn of A, which is the fraction of A's in the observed sequence xn in the raw file, and you treat this as the estimate. So take this as the estimate of Px. Right? So that's what we typically do. But sometimes maybe you don't want to count the fraction of A's in the entire file. Right? So this would mean that you have to go through two passes of the entire file. You have to read the entire file twice. Maybe you don't want to do that. Sometimes you want to design the code on the fly, or maybe at the time of estimation you don't have the entire sequence xn, you only have a part of it. So maybe your estimate is off. You estimate it as qx instead of px. So qx is maybe roughly close to px, but not exactly the same as px. If n is large, then the empirical frequency is going to be close to px. But then if you try to estimate using a very small number of samples, maybe the first 100 samples or so, then your estimate is going to be off. Right? So suppose that our estimate is qx, whereas the true distribution is px. Okay, and we use this to design let's say the Shannon code. Okay, so you use qx to design the Shannon code. Right, so L of x is now going to be the seal of log 1 over q of x, right, which is going to be different from log 1 over p of x. So in this case, what is the expected length going to be? What is the expected length going to be? Yes, anyone? The true distribution is px. Yes, Nadeem?
It will be the frequency of.
Can you maybe speak up? I can't hear you.
Yeah, it will be the frequency of occurrence of mu xa multiplied by the seal of log to the base 2 when divided by qx.
Okay, so well, mu of x, or let's say it's the true distribution, p of x. Right, so this is the true distribution. So that's what we call p of x times, well, we're choosing the lengths according to log 1 over q of x. So as you have rightly pointed out, it is log 1 over q of x. Oops. Just give me a minute. Right, so the expected length is going to be summation over all x, p of x times L of x, which is log 1 over q of x, because we're choosing the lengths according to log 1 over q of x, because our estimate is q of x instead of p of x. Okay, so we know that this is going to be less than or equal to the seal of something is going to be less than or equal to this plus 1. So it is p of x times log 1 over q of x plus 1.
Sir,
Yes.
can you explain why did we take the true distribution?
Oh, q distribution, because suppose that you don't know that the true distribution is px. Okay. So for example, one way to find the true distribution is to count the frequency of occurrence of symbols of the frequency of occurrence of every symbol in the entire file, right? But maybe you don't want to do that, or you're not able to do that, and you take the frequency of occurrence not in the entire file, but maybe the first half of the file or 1/4 of the file. So for whatever reason, you have a bad estimate of the true distribution, and your estimate is qx. The actual distribution is px, but then you have estimated it wrongly as qx, some other distribution.
Sir, then while calculating the expected value, why are we
Uh-huh.
not considering QX and why are we taking it to be PX?
Because the true distribution is qx, is px, right? You're looking at, so let's take the following maybe simple example. Suppose that okay, so suppose that you have a sequence. It's maybe bad, but let's assume that there are three symbols, A, B, and C. The actual distribution is kind of uniform. Okay, so if you look at the entire file xn, then there are roughly n over 3 A's, n over 3 B's, and n over 3 C's. Okay. But then if you look at maybe the first half of the file, so this is the entire sequence xn, you maybe look at only the first part. So for the entire file, you're going to have it's 1/3, 1/3, 1/3. But maybe if you look at only the first part of the file, the first 1/3 or first 1/4 of the file. So in this part of the file, maybe the frequency of occurrence is 1/4 of 1/4. That can happen, right? If you look at a small enough chunk, then it can be different from the overall distribution of symbols. You agree?
Yes, sir.
Okay. So now you design a code according to this particular distribution. So basically you would assign lengths of 2, 1, and 2, because log 1 over px is log 1 over log 4, log 2, and log 4 respectively. So that is 2, 1, and 2. But then what is the total compressed length? It is basically summation the number of A's in the entire file times 2 plus the number of B's in the entire file times 1 plus the number of C's in the entire file times 2. Right, so this is the compressed length. But what is the number of A's in the entire file? It is not n by 4, right? It is n by 3 times 2 plus n by 3 times 1 plus n by 3 times 2. So it is p of x, so n times p of x times L of x instead of n times q of x times L of x, because for the overall file, the frequency of occurrences is roughly p of x, not q of x.
Yes, sir, got it.
Okay. Okay, so since CL of log 1 over q of x is log 1 over q of x plus 1, this is basically just summation of x P of x log 1 over Q of x plus 1, because summation P of x into 1 is P of x and summation overall x of P of x is 1. Right, so it's basically this quantity. Now, I want to express this in terms of the entropy, the true entropy of x. The true entropy is h of px, right? So I can write this in the following manner. P of x log, let me multiply and divide by P of x. Q of x into 1 over P of x plus 1. Now I can split the two terms in the log. Summation overall x of P of x log P of x by Q of x plus P of x log 1 over P of x plus 1. So what's the second term? The second term is basically just the entropy h of x, right? So this is what we would, this is the best compression length that we can hope for if we knew the true distribution. All right, but now what is the second term equal to? What is this term equal to?
KL divergence.
It's just the KL divergence between P and Q. So just to be clear, let me use, instead of just saying h of x, let me call this h of px plus 1. Right, so this would be the expected length. So the expected length is equal to this particular quantity. This is the best we can hope for, right? This is a penalty because that we have to pay because of the Shannon code. So this is less than or equal to this. But then this is an extra penalty that we have to pay for not knowing px, for wrongly estimating px as qx. Okay, and you know that the KL divergence is always non-negative. So this quantity on the right is always going to be strictly larger than, if px is not equal to qx, then this is going to be strictly larger than h of px plus 1. Right? So the penalty for not knowing the correct distribution is exactly equal to the KL divergence. So that's another interpretation of the KL divergence. It is the additional penalty you have to pay in terms of the in terms of the compressed length if you estimate px wrongly as qx. So if you code according to qx, when the true distribution is px, then the expected length becomes larger, and it becomes larger exactly by this amount. Right? Any questions? Okay, so we've now seen Shannon codes in some detail, and we've seen that it's not exactly optimal. It's close to optimal. It gets you somewhere within h of px plus 1 bits, but it's not very efficient to design the Shannon code in the first place. You have to look at this tree and then find the code words in a very greedy fashion, and so on. So is there a better way of designing a code which is also optimal, something which you cannot beat? And in fact, there is, and we'll see that now. So we now see another class of codes, variable length codes, called Huffman codes. And these Huffman codes are going to be optimal in the sense that no matter how you try to design the code, the Huffman code will always, among all possible prefix-free codes, the Huffman codes achieve the minimum possible expected length. Okay. So what is the Huffman code? Let's look at it through an example. All right. So let's take maybe the following example. Let's say that the distribution Px, the probabilities are, let's say, 0.4, 0.2, 0.1, 0. Let's take this to be maybe 0.3, 0.1, 0.1, maybe 0.2 and 0.1. Okay. Okay, yeah. So 0.4, 0.3, 0.2, and 0.1. So if let's first try to construct the Shannon code for this particular example. So what are the lengths going to be?
Two.
2.
Again
So
two.
2.
Okay. So
Two, two,
second one
three.
is also 2. 2, 2,
3, 4.
3, and 4. Is it? Oh, fine. So 2, 2, 3, and 4. So one, the Shannon code. I guess very quickly drawing the tree, these would be the code words. So this would be one code word. Let's call this A, B, C, and D. So this would be for A. B, the third symbol has length 3. So this would be C. The fourth one has, I guess, 4. So this would be D. Okay. Well, clearly this looks bad, right? You can definitely at least assign C to this particular code word and D to this particular code word and get a smaller expected length. Okay, but still this still performs okay because it's within 1 bit of the entropy. So let's see what Huffman codes do. So I'll explain Huffman codes using an example, using this particular example. So the Huffman coding procedure is the following. You list all the probabilities in descending order. Okay, you list all the probabilities in the descending order, and at every step you merge the two least probable symbols to form a super symbol. Okay, and then you sort of keep proceeding further. So the intuition is the following. Let us look at the code tree. Okay, let us look at any possible code tree. Take two symbols. So one intuition is that the symbols with the least probability should get the longest code words, and symbols with higher probability should get shorter code words, right? So the code word length should be kind of inversely proportional to the probabilities themselves. So if the probabilities are higher, then they should get shorter code words, and if it's lower, then they should get longer code words. So let's look at the two least probable symbols, okay, and let's assume that they get the longest code words. Now if I merge these two to get a super symbol, then you can think of this as the code word corresponding to this super symbol obtained by merging these two symbols. And what is the probability of the merged symbols? It is just the sum of the probabilities. So in this case, let's see what happens. So the two least probable symbols are C and D. Okay, so I'll merge these two symbols to get one super symbol of probability 0.3. Okay, I get one super symbol of probability 0.3. The remaining are as it is. I don't touch the other symbols. Now I do this once again. So now this is my new alphabet, A, B, and whatever the super symbol is. Let's call it C1. Now I'll merge the two least probable symbols. Now in the new alphabet, the least probable symbols are B and C1. So I'll merge these two. Okay, I'll merge these two. The probability of the merged symbol is 0.6, right? And now I have only two symbols left, so I'll merge these two as well. So I'll keep merging the two least probable symbols until I can't do it anymore. I have exactly one symbol left. All right. Now, if you look at this kind of looks like a tree, right? So if I reorient this, I have C and D. So I'm going bottom up. So I have C and D, which are the least probable symbols. I've merged them to get one super symbol of probability 0.3. And then what did I do? I merged B and this super symbol to get another super symbol B. So this has probability 0.6, and I merged, had one more symbol A. I merged A and this particular symbol to get sort of the super symbol, and I can't go further. All right, so this had probability 0.4. Now B has had probability 0.3, C had probability 0.2, and D had probability 0.1. So now this looks like a code tree on its own, right? So let's assign code words. So let's assume that this is 0, 1, 0, 1, 0, 1. So what are the code word lengths? So A gets mapped to 0. The code words are 0, 1, 0, 1, 1, 0, and 1, 1, 1. Okay, so these are so this is the code obtained using this particular technique by merging two symbols of the least probability. You keep doing this in a one after the other. At every step, you merge the two least probable symbols and go on till you can't do it further. So this gives you a tree of this form, and this looks like a code word tree. So let's treat this as the code word tree itself. Okay, is this example clear? So let's take another example. Okay, so let's just keep this in mind that this is the code for this is the so-called Huffman code. Okay, So this is the Huffman code. So let's maybe also calculate the expected length. What is the expected length going to be in this case? So it is 0.4 into 1 plus 0.3 into 2 plus 0.2 into 3 plus 0.1 into 3. Can someone calculate and tell me what this is?
1.9.
Okay, so 1.9 bits. Okay, so this was the same source for which we drew the Shannon code, and looking at the Shannon code, we realized that C and D could be given shorter symbols, right? So if we did sort of a greedy procedure, then and we sort of shortened the code words for C and D, this is what we would get. C and D, right? So I just assign this code word to C and this code word to D. So in this case, what is the Shannon code, of course, achieves a much larger expected length, but now the sort of optimized version of the Shannon code, what would be the expected length for this?
2.
2 bits, right? So as we can see, in this case, we've done even better than that, right? So we designed the Shannon code and then we assigned shorter code words to some of the symbols just by visual inspection, and that gave us an expected length of 2 bits. But now we're doing even better. We're doing less than 2 bits. It is 1.9 bits. So the Huffman codes can do even better than, much better than Shannon codes, of course. So let's look at another example. Let's take the following symbols. So let's say the probabilities are 0.25, 0.25, 0.2, 0.15, and 0.15. There are 5 symbols, right? Of course, there's the probability sum to 1. So let's do this procedure. We have A, B, C, D, and E. So which are the 2 least probable symbols? They are D and E. So I'll merge these 2 to get a single super symbol of probability 0.3. Okay, so now which are the 2 least probable symbols? Which one should I merge?
B and C.
Exactly, so B and C are the least probable symbols, so I'll merge these 2. Okay, so I'll merge these 2 symbols. I get a single symbol of probability 0.45. Now, which are the 2 least probable symbols? Which probabilities should I merge?
0.25 and 0.3.
Exactly, so it's 0.25 and 0.3. So remember the symbols now, I have 3 symbols. This is one symbol, this is one symbol, and this is one symbol. So I'll merge the 2 least probable symbols, and those 2 are 0.25 and 0.3. So I get 0.55. And now I have only 2 symbols left, so I merge these 2, and so this is what I get. So let's sort of draw this in terms of a tree. So I started out with merging D and E. I had D, I had E, I merged these 2. And the next step, I sort of merged C and D. C and D, sorry, I guess B and C. B and C. And then I merged A and this particular super symbol. So A and this, and then I merged these 2. Right? So So this is what the code tree would look like. So I assign 0, 1, 0, 1, 0, 1, 0, 1. So the code words for A, B, C, D, and E, they would look as follows. So what is it for A? It is 1, 0. For B, it is 0, 0. For C, it is 0, 1. For D, it is 1, 1, 0. And for E, it is 1, 1, 1. What is the expected length?
Two point five.
Okay, so 2.5 bits. All right, so the expected length is 2.5 bits.
2.3, sorry.
2.3 is it? Okay. 2.3. So it's 2.3 bits. Now, if I didn't do any sort of compression, if I just had to represent these using bits, fixed length compression, zero error, how many bits would I need? Fixed length, zero error, no compression, basically.
3 bits.
Right? I need at least 3 bits. So we're doing much better than that. It's 2.3 bits. Okay, so this is basically the Huffman coding procedure. You keep merging two symbols, and then until you can't merge two least probability symbols, until you can't merge any further. Now, although the code tree, in some sense, you can get a code tree, remember that the labeling is not unique. You could label this in any other way. So one way to label it would be, so I have this one. I could label, I guess, A gets 1, right? So I could label this as 0 and this as 1, and maybe this as 1 and 0, and I guess 1 and 0 and 1 and 0, right? So then A would get assigned the code word 0, 1, and B would get assigned 1, 1, C would get assigned 1, 0, D would get assigned 0, 0, 1, and E would get assigned 0, 0, 0, 0. Right? So at least even though you have the same code tree, the code words assigned could potentially be different. Okay. So it's not exactly clear what the best way to do things are. All right. But nevertheless, at least in this particular example, the expected length remains the same no matter how you label these, and the code word lengths also remain the same. Okay. So no matter how you label the tree, the code word lengths will always remain the same. Now it's also possible that the code word lengths could also be different. There could be two different way of constructing Huffman codes for the same probability distribution, but the expected length nevertheless will remain the same. So let me see if I can cook up such an example. So remember, we're always merging the two least probability symbols, right? But then it is not clear which two symbols should be of the least probability. If there are three symbols with the least probability, with the same probability, and that is the smallest, then you could merge any of those, right? So for example, let us assume that let's take the following distribution. say 0.1, 0.1, 0.1. So this is 3. Say 0.2 and 0.3 maybe. Maybe one more. Yeah, so this is better. 0.2, 0.3. Right. So say that this is A, B, C, D, E, F. Now at the very first step, it's not clear which ones you should merge, right? I could merge E and F, or I could merge D and E, correct? And merging E and F could give you one set of code word lengths. Merging D and E could give you another set of code word lengths. So let's try one thing. So let us merge E and F. So I get a super symbol of probability 0.2. Now, which are the two least probabilities? Two smallest probabilities?
0.1 and 0.2.
0.1 and 0.2. But now again we have multiple choices, right? We could merge this 0.1 and this 0.2, or this 0.1 and this 0.2, or this 0.1 and this 0.2. Right? And each of them is going to give us a different code with different sets of code word lengths. But anyway, let us merge these two for now. So I merge these two, I get 0.3. And now the two least probabilities are 0.2 and 0.2. So I merge these two, get 0.4. So now the two least probabilities are 0.3 and 0.3. So I will merge these two to get 0.6, and these two get 1. Okay. So in this case, the code words are the following. So let's look at the code word tree. I first merged E and F. E and F. Or maybe let me try to just label this tree itself. That will make it easier. So I'll just label this 0, 1. Zero one, 0 1, 0 1, 0 1, 0 1. B, C, D, E, F. So what is the code word for A?
0 0.
It's 1 0, right? So it is 1. So look at the path from this point to A. It is 1 0. What is it for B? It is
0
this
0.
path, so it's 0 0. For C, it's
0
0 1. For D,
1
it is
1
1 1 0. For E, 1 1 1 0. And for F, it is 1 1 1 1. So this is one code, right? This is one possible Huffman code for this source. Can you compute the expected length? So the lengths are 2, 2, 2, 3, 4, and 4. And the probabilities are 0.3, 0.2, 0.2, 0.1, 0.1, 0.1.
2.5.
2.5, is it? Okay, great. So 2.5 bits. Okay, good. So now let's try to construct a different Huffman code for the same source. Right, what do? I merge the two least probable symbols. Let's say that I merge these two. Okay, I get 0.2. Now I have a choice. I can merge these two symbols. So last time I merged these two. This time let me merge these two symbols. So I get 0.3. Now the two least probable symbols are this and this. So let me merge these two. I get 0.4. Now which one should I merge? It is this and this. So let me merge these two. This is 0.6. And now I merge these two and I get 1. So let me again label these 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. D, C, D, E, F. What is the code word for A?
One one.
1, 1. For B? It goes
0,
this
1.
way. So 0, 1. For C, it is 1,
101.
1, 0, 1. For D,
100.
1, 0, 0. For E, it comes this way 0,
401.
0, 0, 1.
All zeros.
And it is 0, 0, 0. Right? So now the code word lengths are different. So I got 2, 2, 3, 3, 3, 3. In the previous case, I had 3 code words of length 2, 1 code word of length 3, and 2 code words of length 4. But now by merging it this particular way, I get 2 code words of length 2 and 4 code words of length 3. Now, what is the expected length?
2.5.
It's still going to be the same. It will be 2.5 bits. So there could be, so in Huffman coding, there could be 2 different ways of merging symbols. So you get 2 different Huffman codes for the same source, but the expected length will be the same. It won't change. No matter how you merge the symbols, as long as you're merging 2 symbols of the least probability, doesn't matter which ones you choose, you will still get the same expected length, and it will be equal to 2.5 bits. So or it will be the same. All right, any questions?
Sir,
Yes.
um, like there is one more way, no, sir? Like trying to divide the set of probabilities into like equal half and
You mean a different strategy for coding or a different Huffman code?
no, sir. Just for grouping, I'm asking. That's all. Not
Okay,
just
so
same.
sure, sure. So I guess it's a different strategy. So here what we are doing is we are sort of grouping symbols together, and the way we are grouping is based on the least probabilities. You group 2 symbols of the least probabilities to form a super symbol, and then so on. So it's sort of a bottom-up approach. All right. Uh, but what you can think of, so for example, if you have ever encountered maybe clustering, it's similar. I mean, the approach feels similar to linkage based clustering methods. But anyway, if you're not familiar with it, doesn't matter. But there's a different approach. So that is a more top down approach, and that is the following. You have the set of symbols A, B, C, D, E, F. What you can the same probability. Okay, so roughly probability half on one side, probability half on the other side. Okay, so you group these into two groups, And then you keep doing the same for each group. So split each group into two subgroups such that the two subgroups have roughly the same probability, and so on. You keep proceeding till you have only one symbol in each subgroup. Okay, so this is what is also sometimes called a slice code, and it's a more top-down approach, right? So instead of merging symbols together to get super symbols, you're treating this whole thing as one super symbol and trying to split the super symbols into sort of two super symbols, each having roughly the same probability. All right. So in other words, you're kind of trying to slice each super symbol roughly in between, right, into two equal halves. So the Huffman code is kind of merging, whereas this is splitting, and splitting. This is definitely another approach, but it turns out that this is not always optimal. It doesn't get you the smallest expected length. On the other hand, we will show that Huffman codes, among all possible prefix-free codes, achieve the least expected length. Okay. Is that any questions?
Hello, sir.
Yes.
Yes, Huffman code by efficient does it mean it approaches entropy?
So I will give the exact statement now.
Okay.
So as I said, it achieves the minimum expected length among all prefix-free codes. Not necessarily equal to entropy, because we also saw that if the source is not dyadic, then no prefix-free code will attain entropy. It's going to be above entropy, somewhere between entropy and entropy plus 1 bits. We don't know exactly what that number is for arbitrary sources, but if the Huffman code achieves a certain expected length, maybe h of x plus 0.1, then it is impossible to achieve any expected length less than h of x plus 0.1 using a prefix-free code, using any other prefix-free code.
Okay, sir. Understood.
Right. Right. So we'll prove that particular statement. But any questions so far? Right. So now what do we want to show? We want to show that Huffman codes are kind of the best. You can't do any better than Huffman code. There may be another code which achieves the same performance as Huffman codes, but no matter what you do, you can't do better than the Huffman code, right? Because we just saw that for the same source there can be different Huffman codes itself, right? So obviously the best code is not unique, but there's definitely the best minimum expected length. And in terms of the in terms of the expected length, you can't do better than any Huffman code. So let's say L star of Px. So for a given source, so for a given probability mass function Px, let this be the minimum expected length among all prefix-free codes. So the minimization is performed among all prefix codes. So far, all we have shown is that this is greater than or equal to the entropy, but we don't know what exactly that number is going to be. And it's impossible to find out what exactly that number is going to be. And since Shannon codes achieve something less than h of x plus 1 bits, we know that L star of Px, So it's going to be in general greater than or equal to h of x, and it is going to be less than or equal to h of x plus 1 bits, somewhere in between. We don't know where. Okay. So this is the minimum over all possible prefix-free codes. And now let me define LH of px as the expected length for any Huffman code. So the claim, what we want to prove is that LH of px is equal to L star of px. So the expected length achieved by the Huffman code is the minimum among all possible prefix-free codes. Okay, is that clear? Any questions? Okay, so in order to prove this, we'll use some properties. Now, here's a claim. We'll prove this in the next class. Now, given any optimal in the sense of achieving the minimum expected length prefix code, we can construct another optimal code with the following properties. One, if px of a is greater than px of b, well, this has to be satisfied by all optimal codes. The length of a should be, the length of the code word for a should be less than or equal to the length of the code word for b. That's obvious. Two, two symbols of the least probability have the longest lengths and are equal. So if you look at the two longest code words, then both of them have the same length. And the third is the two longest code words they differ only in the last bit. Now these two properties are satisfied, we'll see that these two properties are satisfied by all optimal prefix codes, but then this is not satisfied by all prefix codes, by all optimal codes, but then you can always construct an optimal code which satisfies the third property as well. Any optimal code, I'm not talking about Huffman code specifically. You take any optimal code, you can always find an optimal code with these three properties. And of course, the expected length is the minimum. Okay. So we'll prove these three statements, and we'll show that any code which satisfies these three properties must have an expected length which is the same or greater than the Huffman code. Okay, so we'll stop here. If there are any questions, then I can take them now, or otherwise we'll meet in the next class.
So just a small observation.
Yes, Sunil.
So for like the Huffman code, we are like clubbing up the lowest two probabilities and all.
Correct.
So let's say like we have 6 symbols. So
Mhm.
the number of symbols is between 2 raised to k and 2 raised to k plus 1. So can't we?
Okay. Okay.
So if we just draw a binary tree of length k plus 1, then
Okay.
start filling from the bottom just to prove the Kraft's inequality. If we have, let's say, 3 symbols, then 2 symbols of level 2 and 1 symbol of level 1, like that. And then assign
Okay.
probabilities, the least ones on the bottoms and the highest ones on top directly. That one also lead to a like optimal Huffman code only.
So I'm not sure. That's not true, right? So what did you say? So let's take 6 symbols.
Yes, sir.
So what? So you want to draw a code tree of what length?
So 6 is between 2 square and 2 cube.
Okay.
So 2 raised to 3. So take the length 3 because
Okay. So you take length 3.
uh, so you just start. So you have 6 symbols. You fill the bottom 2 leaves. Just any bottom 2 leaves.
Okay.
Yeah. So and then fill any 2 more.
You fill in. So which ones now you fill?
Anyone's you see you fill the
These
next one,
these
yeah,
two.
these. So then
Okay.
the top two, the level, the upper level of the
Mm-hmm.
next subtree, the 2 ones.
You mean these two?
No, not these two, the
Oh,
next
these two. These two.
these two. And
Okay.
then just assign the probabilities from the low, like uh, so the least probabilities to the bottom leaves, and then increasing order to the upper leaves in any order.
So basically, if you have 6 symbols, then the code tree will always look like this, right?
Not always look like this, but like Huffman tree also has, Huffman code also has different like possibilities, right? So this one will give
Correct. But you're sort of
one
fixing the depth here, right? You're fixing the depth to be 3, correct?
yes, sir.
Okay. Basically, if you have 6 symbols, you will only look at a tree of depth 3. Did I get that right?
Yes, sir.
Okay. Um, and and now how do you decide whether you want to? Okay, so in this case, this will be the tree.
So it's just some empirical idea, like
Agree.
the 2 ones will sum up to like 1/4 plus 1/4 will get 1/2, and 1/2
Mhm.
clubbed up with the 1/2 will get 1. Just
Okay.
summing up to 1
Okay. Okay.
empirically. We could
Okay.
take any of the leaves and then accordingly select the nodes on the upper level.
Okay. But okay. But this will not always work. So this might give you an expect. So this will, of course, it will give you a prefix-free code. There's no doubt about that. But in terms of the expected length, this won't be the best. So let's look at a case where this may not do well. Let me take
Sir,
the yes,
so this what he said, this tree.
yes. Uh-huh.
So will it be? Will this approach be like that clustering one which you said, or?
I mean, sure, this is one thing, but then the connection to clustering, which I mentioned, was pretty loose. It's just a merge. You just merge symbols at each step. But here it's okay. So again, maybe let me try to address Soham's question first. So let's take the following distribution. So half. So 6 symbols, right?
Yes, sir.
So half, 1/4, uh, 1/8, 1/16, 1/16. How much more do I have left? 1/3
I guess it's 10.
right. So sorry, 1/32 and 1/32. So this sums to 1, right?
Yes, sir.
Okay, great. Now if you have 6 symbols, then this is the code tree that you propose, right?
Yes, one of the possible.
Is there any other possibility?
Yes, sir. Like based on how you fill the leaves, you have to select the nodes on the top.
Uh, sure. Okay. So is this so for
Just to
six
make it
symbols?
perfectly.
So for 6 symbols, and a code of depth 3. Is there any other way to sort of fill it? I mean, forget about relabeling. So there'll be 4 code words of length 3 and 2 code words of length 2. Right?
Yes, sir.
You can't get anything else.
Yes, sir. Right.
Correct.
That thing only.
Yeah.
Excluding
Yeah,
relab.
forget about relabeling. That doesn't matter. I'm just talking about the code word lengths. That's what I'm. That is because that is ultimately that is all that is important, right?
Yes, sir. Right.
So basically, the 4 smallest will get lengths 3,
3.
and the 2 highest will get length 2. Correct?
Yes, sir.
So what is the expected length in this case?
I think 2.25.
2.25. Right? Okay, fine. 2.25. Okay, great. What is the entropy of this going to be?
Yeah, 2.5.
It's whatever. It's going to be strictly less than 2.25 bits. Maybe around 2 bits. I'm not sure. You'll have to check. But if you try to draw the Huffman code for this, it's not going to look like this. It's going to look like this. 1, 2, 3, 4, 5, 6. So this is going to be A, B, what it is. If you label the probabilities, it's going to be half, 1/4, 1/8, 1/16, 1/32, and 1/32. So the Huffman code is going to be a tree of depth 1, 2, 3, 4, 5. It's going to be a tree of depth 5. So that's why it's not enough to just stop at a tree of depth 3. It's if you want to look for the optimal code, then in fact you have to look up to trees of depth. So if this has m symbols, you have to look up to trees of. If you want to search for the optimal code, in some sense, then you have to search for trees up to depth m-1, not just log m or ceil of log m.
Got it, sir.
Right? Because this is so for probabilities which are roughly balanced, that is close to being the same. Some of them are a little higher, some of them are a little lower. Such sort of roughly balanced trees will work. Whereas in this case, the probabilities are very skewed. There are some symbols with a high probability, and there are some symbols with a very low probability. For sort of geometric kind of distributions, the tree is also going to be correspondingly very skewed, and the tree will have a very large depth.
Yes.
So anyway, you calculate this, you'll see that this, if you try to construct the Huffman code, it's going to be optimal. It's going to achieve an expected length equal to the entropy, whereas this one won't get you the entropy. It will be something much higher. All right.
Yes, I got it.
Good. Any other questions?
Thank you, sir.
Any other questions? Okay, if not, then we'll stop for today. See you all next week.